Welcome to today's class on graph theory. Today we discuss the five-color theorem. Theorem says that every planar graph is five-vertex colorable. So we prove this. Proof. Proof is by contradiction. By contradiction. Suppose that the theorem is false. Then there exists a six critical plane graph G since a critical graph is simple. We have delta less than or equal to 5. This is by corollary 9.5.7. On the other hand, delta is greater than or equal to 5 by theorem 8.1. Therefore, delta equal to 5. Let V be a vertex of degree 5 in G. Let V1, V2, V3, V4, V5 be a proper 5 vertex coloring of G minus V. Such a coloring exists because G is 6 critical. Such a coloring exists since G is 6 critical. Since G itself is not 5 vertex colorable, V must be adjacent to a vertex of each of the 5 colors. Therefore, we can assume that the neighbors of V in clockwise order about V are V1, V2, V3, V4 and V5, where Vi belongs to Vi for 1 less than or equal to I less than or equal to 5. That is, Vi is of color I. That is, this is a situation. You have the vertex V. So this is V1. This is V2. This is V3. This is V4. This is V5. Denote by Gij the subgraph G induced by Vi union Vj. Induced by Vi union Vj. Now, Vi and Vj must belong to the same component. Of Gij. For otherwise, what happens is, suppose that this is Vi and suppose that Gij is a component which contains Vi, and that suppose that it does not contain V2. Vj. Suppose that this is Vj and this is Vi. Then you have vertices like this, some Vk, so that the color of this is I and the color of this is J and the color of this is I, etc. Then you recolor this by interchanging the colors I and J, so that this will become Vj. So this is actually Vj is V2, so this is actually V2. We have used the colors 2, 3, 4 and 5 to color the neighbors of V. So which is not possible, because our assumption is that neighbors of V in clockwise order about V are V1, V2, V3, V4 and V5, where Vi belongs to Vi for 1 less than or equal to I less than or equal to 5. So for otherwise, consider the component of Gij containing Vi. By interchanging the colors I and J in this component, we obtain a new proper 5-vertex coloring of G minus V, in which only 4 colors, so all but I, are assigned to the neighbors of V. We have shown that this situation cannot arise. Therefore, Vi and Vj must belong to the same component. Of Gij. So let Pij be a Vi Vj path in Gij, and let C denote the cycle V1, P13, V3V. So this is the situation. So you have V is here. This is V1. This is V2. This is V3. This is V4. This is V5. You consider a path P13 joining 1 and 3. So this is the path P13, and this is cycle V, V1, P13, V3, V. This is the cycle C. So from this you can see that C separates V2 and V4 because V2 belongs to the interior of C and V4 belongs to the exterior of C. Therefore, by Jordan curve theorem, a path P24. So a path P24. So suppose that this is the path P24. P24. This must meet C at some point. Since G is a plane graph, this point must be a vertex. Meeting point must be a vertex. So this must be a vertex. Suppose that this is the vertex X. As it is a part of the path P13, its color must be either 1 or 3. And since it is a part of the path P24, its color must be either 2 or 4. So that is not possible. So we get a contradiction. So this contradiction is due to our assumption that the planar graph is not 5 vertex colorable. So we'll write these things. Now since C separates V2 and V4, this is because since V2 belongs to interior of C and V4 belongs to exterior of C, it follows from Jordan curve theorem that the path P24 must meet C in some point. Because G is a plane graph, this point must be a vertex. But this is impossible since the vertices of P24 have colors 2 and 4, whereas no vertex of C has either of the colors. So we get a contradiction. This proves the 5-color theorem. So that's all for the day. Have a nice day.